In this problem from section 14.4, we want to find the mass and center of mass of the region bounded by R, where x is greater than or equal to 0, 3 is less than or equal to y, and less than or equal to 3 plus the square root of the quantity 9 minus x squared with density rho of xy equals x times y. What I'd first like to do here is sketch the graph of the region, and then we're going to use that when we determine our bounds of integration. For the graph of x is greater than or equal to 0, we're looking at the right half of, to the right of the y-axis. And then we want to look at this inequality to determine the bounds. Right here, 3 is less than or equal to y. That means the bottom of the region is y equals 3. And y is less than or equal to 3 plus this quantity. That means the top of the shaded region is y equals 3 plus the square root of 9 minus x squared. Now let's take a look at the graph of this. Again, x greater than 0 just means you're looking to the right of the y-axis. The line y equals 3, 2, 3. And the graph of y equals 3 plus the square root of 9 minus x squared, that ends up being a portion of a circle. In fact, if you plug in 0, you get 6. Okay, and if you plug in 3, here you get 3. So we have the shaded region here is our planar lamina, and the density is given here. The density is equal to x times y. So as x and y both increase, then the density will also increase. To determine the mass, we want to set up a double integral where mass is a double integral over the region R of density, which is your rho of xy, times your differential area, times dA. Now in this case, our density function is given as x times y, and our differential area can either be dy dx or dx dy. And depending on the order, we're going to determine the proper bounds. To find those bounds, we want to draw a representative rectangle. You can do either vertical or horizontal. I'm going to go ahead and use a vertical rectangle. That differential area of that rectangle, this little part here is your dx, the longer part here is your dy. So the differential area, the area of that rectangle, is the length times the width. That's going to be dy times dx. So we need to determine the bounds of integration for our bottom y to the top y. In fact, we already have the bounds right here given to us in the inequality. Your bottom y equals 3, the top y is equal to this 3 plus the square root of 9 minus x squared. And then we also need the bounds for x. The left x, so if you slide that rectangle all the way to the left, that x value is 0. And the right x, slide that rectangle all the way to the right, and that you get x is equal to positive 3. So we're going to use these as our bounds and substitute in our density function and the differential area as dy dx. So the mass is going to be a double integral where the density is x times y. The differential area is dy times dx. Our inside bounds are bounds for y, which go from 3 to 3 plus the square root of 9 minus x squared. And our outside bounds are for x, and x goes from 0 to 3. Now we want to integrate this, beginning with the inside integral. The differential is dy, so we integrate with respect to y. We treat y as a variable and x as a constant. That antiderivative is xy squared over 2. And our bounds are from y equals 3 to y equals 3 plus the square root of 9 minus x squared. And then we would evaluate that and then set that up as a single integral dx. And let's continue on. When we substitute in the upper bound, we're going to get, we replace the y with the upper bound to get x times the quantity of 3 plus square root of 9 minus x squared squared, all divided by 2, minus what you get when you plug in 3. And for y, 3 squared is 9, so this is the same thing as 9x over 2. So this is now a single integral from 0 to 3 of this entire quantity dx. Now this is would likely take quite a while to calculate by hand, so let's go ahead and use a graphing calculator to determine this integral. When we use the integration feature of the graphing calculator, it is important to make sure you have all the parentheses in the correct places. So on this calculator, I'm going to choose the command to integrate the function where the lower bound is 0. Move the arrows to get to the upper bound of 3. I'm going to write this as x, using parentheses here, 3 plus the square root of 9 minus x squared. Use the arrow to get out of the parentheses. Oops. Close the parentheses here, and then that quantity is squared, and we divide that by 2 minus our 9x divided by 2, and the differential is x. Let's press enter, give it a minute, and get the decimal approximation. So when you evaluate this definite integral, then it's 37.125 approximately. So that's the mass of this planar lamina. Now to find the center of mass, we need to come up with two more integrals, the moment with respect to x and the moment with respect to y. When we set up those integrals, the bounds are going to be the same. The difference is going to be in what is inside the integral. Okay, what I've done is I've erased the work so I can continue on this page and show you the remaining double integrals for the moments. Let's find the moment with respect to the x-axis is a double integral over the region R of the distance from the y-axis. Actually, let me go back a second here. Let's make it the moment with respect to the x-axis is a double integral over the region R of the distance from the x-axis, which is y, times the density rho of xy times the differential area. Now when we set up this integral, our bounds are going to be the same, the density is the same, and the order of the differentials is going to be the same. The only difference is that we're going to have this y included, so that's going to change the value of our integral. So the integral is the integral from 0 to 3 of the integral from 3 to 3 plus the square root of 9 minus x squared of y times the density, which is x times y, times the differential area, which is dy dx. Now the solution in solving this, working this out, is similar to the one we just did, except here you're going to have a y squared. You integrate with respect to y, it's going to be y cubed over 3. So you can work through that, and when you use a calculator to evaluate that, you get that this moment with respect to the x-axis is approximately 157.95. So that we could then move on to our next moment. The moment about the y-axis, or moment with respect to the y-axis, is a double integral over the region R of the distance from the y-axis, which is x, times your density, rho of xy, times your differential area. Now again, this is very similar to our mass double integral and our moment double integral, with the exception that we're having an additional x inside the integral. Our bounds are going to be the same, the density is going to be the same, and the differentials are going to be the same. That x is going to be what's different. So we're going to end up with a different value when we evaluate that double integral. So when we plug that in, the bounds would be the integral from 0 to 3 of the integral from 3 to 3 plus the square root of 9 minus x squared of x times the density, which is x times y, times the differential area dy dx. And again, if you work that out with the graphing calculator, you will find that the moment with respect to the y-axis is approximately 63.9. Now to find the center of mass, we're going to put these together. To find the center of mass, the center of mass formula is found by taking the moment with respect to the y-axis and dividing that by the mass, and the moment with respect to the x-axis and dividing that by the mass. So take those three answers that we found and plug them in. So we get the moment with respect to the y-axis, that was 63.9. Divide that by 37.125, and then take the moment with respect to the x-axis, which is 157.95, and divide that by 37.125. And if we round our final answer to one decimal place, we find that the center of mass is the point 1.7, comma 4.3. And it's a good idea to check whether that point is indeed a point in the in somewhere on the mass itself. So if you check over 1.7 up 4.3, it is a point that's in that region. So we can say that it seems to be correct in terms that the center of mass is in that region. If you do all these calculations and you find that the center of mass isn't even on the region, then you know that you've done something wrong and you can go back and double check your work.